Okay.
You're right, Pamela. I don't know what happened. It went off and on itself.
Yeah.
Now it's back.
All
on.
right. Okay, it's back. Okay, no
Yes.
problem. Thank you. So land use land cover data is, maybe we can have people mute if they're not speaking. Thank you. So it is especially valuable for understanding the impact that many natural and human-induced processes, such as climate change, deforestation, and urbanization can have on the Earth's surface. For example, in these images, you have some destruction, landscape destruction at the top image, and at the bottom, you can see also some activity happening. There's a forest, and then next to it, you have, some burning happening. So it is especially valuable for understanding some of these both natural and human induced processes. So as a result, land use land cover research has been receiving increased attention over the recent decades, and the number of fields that are making use of this data is on the rise. And archaeology is one of the fields that is increasingly making use of spatial data. So the studies of archaeology frequently involve the study of the spatial dimension of human activity over time, and all archaeology carries a spatial component, and therefore the relevance of remote sensing data, GIS data, any geospatial data is actually quite integral with archaeological studies. However, the archaeological and built heritage worldwide is facing escalating threats from a number of factors, amongst them unmonitored urban expansion, large-scale agricultural intensification, and irrigation projects, mainly development projects. So as humanity, as population grows, there's a lot of construction projects, a lot of oil and gas extraction, excessive agriculture, and so on and so forth. And all this actually pose a threat to existing archaeological sites and monuments. So one of the effective means of monitoring threats, or the most effective means of actually large-scale monitoring of these threats, is through land use land cover mapping using remote sensing technologies through the process of image classification. Now, what is image classification? Image classification is based on the idea that different feature types on the Earth's surface have different characteristics in terms of what we call spectral reflectance. So how they behave if their characteristics are captured on a sensor. So they have different spectral reflectance and remittance properties, and this recognition is carried out through the classification process. So in a broad sense, image classification is defined as a process of categorizing all the pixels in an image or raw remotely sensed satellite data to obtain a set of labels, a given set of labels or land cover themes. And we have what you call digital land cover classification, which is quite different from what we have just seen on Google Earth, whereby you sort of visualize. So it's a visualization whereby you can see the difference between a site and the surrounding and tell that this is probably an archaeological site. Now, in terms of digital land cover classification, this is based on the numerical manipulation of digital numbers or brightness values, or what we call radiance. Okay, because you have, as the first speaker, Michael, talked about the electromagnetic spectrum and how we are able to see in the visible part. And so different features on the Earth's surface have certain digital numbers or brightness values, or called radiance. And this is what we manipulate to come up with the grouping of these pixels into a set of labels or land cover themes. And therefore, digital images are composed of picture elements that are called pixels that are located at the intersection of each row and column of an image. So if you look at this workflow here, you have a Landsat image. So Landsat is one of the freely available and the longest term imagery that has been from 1972 and has a 30-meter resolution. So this Landsat image is actually composed of these little squares that are called pixels. And each of these squares, in the case of Landsat, is a 30 meter by 30 meter square, which has a certain brightness value or digital number. So this Landsat image is composed of the pixels on the right, and each pixel has a certain brightness value depending on what that land cover is. So digital image classification involves the mathematical transformation of these digital values to form useful information that relates to land cover types. And the changes in these radiance values in the pixels represent the variation of the land cover surfaces. So if you look at this box at the bottom that has the digital numbers, all the similar features will have the similar digital numbers. So for example, the fourth box on the first row has a value of 200. And if you go further down into maybe the sixth row, you'll also find another 200. And further down into the 10th row, you'll find another 200. So these represent the same land cover class, which could be anything that is found on the surface, any feature that is found on the surface of the earth. So it could be cropland, for example, or it could be an urban center, or it could be a water body, and so on. So this is essentially how digital image classification happens. And this is an example of some of the land use land cover classes that can be found around archaeological sites and which can be used for monitoring. So in this case, you have the map, and then you have the classes. Like you have, the first one is water. And if you look at this map, you'll see blue areas that show water bodies. You also have, built up areas which are showing up in red. And, forest areas, different kinds of forests like the deciduous forest, mixed jungle, evergreen, and then you also have shrubland and so on. So this is some of the classes that you are going to encounter when you're looking at environments around the archaeological sites that would need to be monitored. In particular, for example, the urban areas. So if you'd look, this is a multi-temporal land use for 2013, and possibly if you'd look at an image of the similar area for 2003 that is classified, the built up areas would possibly be much less, not possibly, but definitely be much less because of the obvious growing human population and so on. And also the agricultural areas which are showing up in yellow would be much less, say 10 years earlier. And then it would follow that you'd have forested areas reducing because of the encroaching of human activities. So these are some of the monitoring that can be done around archaeological sites. Now, we also want to talk about the challenges that you could face with image classification, because some people say that classification is easy. It's just something you do. In fact, we have algorithms that you can just click and you get a classification. But is that really the case? Is it as easy as it seems? And then that is a quote by F.C. Bowden, and you also have another quote by W. Blake that says, "A fool sees not the same tree that a wise man sees," meaning that two different people will see two different things, and hence the classification outcomes will be different possibly from one person to the other, depending on how they want to interpret certain features on an image. So what are some of these challenges that we might face during our classification when we want to do monitoring around archaeological sites? So here, the first one I'm going to talk about is the big intra-class diversity. Now, intra-class diversity, what it means is within the same class, you still have diversity. For example, I'm not sure how clear this image that I've placed on the screen is, but essentially what I'm talking about is you have features that are similar. So for example, you have churches. So these are churches at the bottom. The second row here, you have churches, but each church looks different from the other. So essentially, by picking, the pixels that contain one church, it's not a guarantee that it's going to classify the next site which is also a church, as being a church because of the variation of, within the same class. So this is called intra-class diversity. And the same for beaches. You can see the top row, upper right corner, you have beaches that look quite different from each other. But at the end of the day, they are all beaches and you want them to be classified as beaches. But because they appear different from each other and the spectral signature or the characteristic will be a bit different, and therefore this can affect your outcome. The second challenge we'll be looking at is, we'll be talking about is the high interclass. Now this is interclass, which is different from the intraclass. So high intraclass similarity, which is also known as class separability. So are you able to differentiate between a bridge and a basketball court? A bridge and an overpass, and differentiate between a basketball court and a tennis court. So this is, for example, when you're looking at urban areas and you want to be a bit more specific about your built up areas, you don't want to classify them all as built up. So there is a differentiation between the two, but because they're quite similar, and therefore, the separability between the two classes is quite narrow, it becomes also quite challenging to get the difference between those classes. And then the third challenge is the large variance of object or scene scales, whereby you have, storage tanks looking quite different in one image and in the next. Rivers also looking quite different, and so on and so forth. So how do you ensure that you capture all of these as, rivers, or all of these as storage tanks? And then also the coexistence of multiple ground objects. And this is especially a problem when it comes to spatial resolution, which has already been talked about by our first speaker. So when you have multiple ground objects in the same place, for example, you have an industrial area, but you have buildings, you have different types of buildings, you have a road, you have parking lots, and so on and so forth. And then if we're talking about, if we're looking at, say, for example, agricultural areas, and especially looking at agricultural areas in, say, for example, African rural areas, you have quite some landscape heterogeneity there, whereby you have a lot of mixed cropping going on. You have a mixture of agroforestry, so you have trees and crops planted at the same time, and therefore within one pixel you may have different features, and therefore how do you classify this and ensure that you've correctly captured what is a feature in a particular area? And therefore, this brings me to spatial resolution and the mixed pixel challenge. And spatial resolution is a measure of the smallest object that can be resolved by the sensor or the ground area that is imaged for what is called the instantaneous field of view, or IFOV. So instantaneous field of view means when the sensor images the Earth, how much is captured. So this depends on the sensor itself and the sensor characteristics, and how it is constructed in terms of how much can be resolved by that particular sensor. In other words, a pixel represents the spatial resolution. So here we have an example of 4 different types of sensors imaging the same area. So you have the smallest resolution, which is the 1 meter resolution, which could belong to Iconos or even Worldview or any of those high resolution imagery. And then the same area imaged by a 10 meter resolution, spatial resolution sensor, and this could possibly be Sentinel-2, which has 10 meters. And then you have 30 meter for the same area. So 30 meter resolution, you can barely see much. You can see differentiation of pixels, but you can't really make out what exactly it is that feature is compared to A, for example. And then in D, we have really coarse resolution MODIS imagery. Now you can only see big black squares with some differentiation, but in essence, what this shows you is that due to this heterogeneity of that landscape, for example, that you can see clearly in A, you will have a problem of mixed pixels with medium and coarse spatial resolution data, especially in C and D, you can barely see any difference. And therefore, if you look at D, that particular pixel probably contains so many different features. So there could be houses, there could be even a water body, there could be, roads and so on, but you cannot tell because of the spatial resolution of that image. So this is necessary to know because mixed pixels are major causes of uncertainty in image classification process. And then without overcoming this issue, then the possibility of extracting meaningful data remains unrealized. However, I have to add in that you do not always need this high resolution imagery like what you find in A. And there are times that you might actually use D. So, if you're doing global mapping, for example, global scale mapping and monitoring of your archaeological sites, then D can actually be used because, you're looking at what is called a small scale. I mean, a scale over a global area. But if you're going to do more localized monitoring, then you're better off using high resolution imagery like A. So it is really up to, the situation. You have to evaluate it is like fitness for use. We call it fitness for use. What is most suitable for your particular application? And therefore, now we come to the workflow for land use land cover mapping and the common algorithms that you will encounter during your site monitoring. So land use land cover classification is one of the most widely used applications in remote sensing, and the two most commonly used applications or approaches include the unsupervised classification, which is, to make it simple, calculated by software, and then you have the supervised classification, which is human guided. Now, let me just give a definition of unsupervised classification, which is guided by or calculated by software. And so this type of classification is based on the software analysis of an image without the user providing sample classes. And it involves grouping of pixels with common characteristics. And then the algorithm uses techniques to determine which pixels are related and then groups them into classes. So this is unsupervised classification. And supervised classification, on the other hand, is human guided and is based on the idea that a user can select sample pixels in an image that are representative of specific classes and then direct the image processing algorithm to use training areas as references for the classification of all other pixels in the software. And it is based on the use of training data, which can be selected either from high resolution imagery or from ground truth data. Like you go to the ground, you go in with your GPS and collect data and then use this data to come and train your image. So you can use a GPS. You can also use your phone and get some geotagged pictures, which is a commonly used approach right now. And then now use this as prior information to guide all other, clustering within that image. So this is the common workflow whereby you have in the unsupervised, you have the image and then clustering happens. And then you have a post-processing whereby you do some cluster grouping and labeling and then finally carry out an accuracy assessment. And then for supervised, what you have, the difference is you have the supervised training whereby there's the human input of the training data and then the pixel labeling, and then finally the accuracy assessment. So this is an example of unsupervised classification, and this is what is carried out by the software. So this depends on how many clusters the user specifies. So looking at that image on the left, the user can specify, say, for example, by eyeballing and saying, I think I see about 10 major classes. I see water bodies, I see vegetation, I see urban, and so on and so forth. And then specify 10 clusters and then leave it to the software. For example, the k-means algorithm to come up with this particular classification. But then one of the disadvantages is that you have to do a lot of post classification processing to actually determine what it is that has been classified, because you did not know prior. It was done by the software. And then now this is an example of some supervised classification, which is human guided. And these are some of the common classifiers or algorithms that you're going to come across. For example, the most common and the oldest is the maximum likelihood classifier. And it is rarely used nowadays, to be honest, because now people have moved more towards machine learning algorithms, object-based classifiers, and now there's a lot of even neural networks and so on and so forth. So in the first, you have the maximum likelihood classifier, then you have a neural network classifier, then you have support vector machine classifier, random forest classifier, naive Bayes, and then an object-based classifier. And all of these are classifying for the about 8 classes that have been identified previously by the remote sensing analyst. And if you look closely at these, you'll see some differences in the outcomes. So usually it is advisable to do some background work on which classifier is most suitable for particular areas or for particular types of classifications. For example, just as an example, the random forest classifier has been known to be very suitable for, even if you have a few training data sets, it is still been found to do a very robust job at classifying. Unlike, say, for example, the maximum likelihood classifier, which needs a good number of samples in order to come up with a good classification. So it is also good to be aware that you need to do some background work on what classifier you need for supervised classification. Now, what about training data? So for land use land cover classifications, for supervised classifications, you need training data. And these training data, as I've mentioned earlier, are those that you select so as to be able to input them into the algorithm so that the algorithm can then classify the entire image according to the input you've given. So this is usually from ground samples or samples from high resolution image. And they are used for training and testing the models. So usually if, for example, you selected 100 points for each class, so for water, you selected 100 points, for closed forest, you selected 100, croplands 100, and so on and so forth. A common common ratio that is used is a 70 to 30% split, whereby 70% of the 100, or rather 70 of the 100 are used for testing, and then 30 are left back for validation. Also common is the 60-40 split, and also an 80-20 split can be used. But mainly you'll come across the 70-30 or the 80-20 split. And I'll go into this a little bit more when we go into how to assess your classification. So in terms of accuracy assessment, you want to know, I have classified that map. Now, how accurate is it? That is really critical. And it is a point that many miss because they assume that you have a map, it is accurate, and that could not be further from the truth. So how is it? I mean, we want to answer this question because we want users of the map to have an appropriate amount of confidence in it. If the map is perfect.
Very sorry, Pamela, to jump in. I just wanted to mention that we can, you can have another 2 minutes. Yes, because we're running a lot over.
Okay.
Yes, thank you.
Okay, thanks. So we want people to know about how well the map has been classified. So let me just jump into the ways of testing. So we have what you call user, producer, and overall accuracy. And the overall accuracy answers this question, that what proportion of the map is correctly classified? Basically, how accurate is it? Then you have user accuracy, which says, if I go into a map, how likely am I to find a certain class there? And then producer accuracy answers a question of, if an area is actually of a certain class, how likely is it to have been mapped as such. And so this is a confusion matrix. And what this shows is if you go down the column and there's a forest class, this is a forest class, 56 pixels have been accurately classified as forest. The rest have been inaccurately classified in other classes like water, grassland, and bare soil, and so on. And that is essentially how it calculates the class accuracies. So essentially, Azadeh, if you just give me just 2 more minutes on top of the 2, I'll appreciate that. So this is an example whereby within this scenario, the user and producer accuracies for vegetation and bare soil are not quite impressive, because you can see that what was to be classified as bare soil is 0, and its bare soil has been classified here, if you go down this column, as vegetation. And then, okay, so here, if you look at the water class, if you go down this column, 82 pixels have been correctly classified as water in total. So it has been perfectly classified. Vegetation, 12 pixels out of 15 have been correctly classified, and bare soil, 9 pixels out of 11. However, if you look at the overall accuracy, it tells you 95%, you have a 95% overall accuracy, which means it's a great classification. But when you go into now this confusion matrix, then you can start seeing that actually it is the water class that is weighing heavily on the classification and giving you a 95% overall accuracy. And this means you need to really look at both the overall accuracy and also go into the class-wise accuracies. This is, I think, my second last slide. So after you do your overall accuracy, you need now to be able to carry out changes or to look at changes across time around these archaeological sites. You need to classify different years. So this is called multi-temporal classification, and is the classification analysis of remotely sensed data from more than one time period. So for example, you can see here. And then after you've done your multi-temporal analysis, then you can carry out change detection. And change detection is the goal. The goal is to detect or discern those areas on digital images that depict change in the feature of interest between 2 or more image dates. So for example, here you have 3 imagery, the same area classified across different years, 1992, 2003, and 2014. And then now the change is detected using certain algorithms like image differencing. So here you can see you have woodland to water changes, woodland to farmland, and so on. And this can also be depicted by graphical format, which shows you here that certain classes have really grown over time from 1975 to 2002. You have changes occurring like that. So that is in essence what you can do to carry out change detection, classification, and change detection around archaeological sites. So thank you so much for listening. This is a Landsat 9 satellite, which was launched last year in September, and carries on the legacy of Landsat from the first Landsat, which was launched in 1972, and which we greatly use for monitoring of areas in the world. Thank you.
Thanks very much, Pamela. Kezola, do you mind to type your question in the chat box? Because of the time constraint, we've been already running a bit over, and now, and I'm afraid that it's going to be too late for our colleagues joining us in South Asia. So if you don't mind to type your question, and Pamela will answer your question in the chat. Pamela, would that be okay?
Yes, that's perfectly okay.
Great.
Thank you.
Excellent. Thank you. So our next speaker, we have to, because of the time again, make an adjustment. Jonas is going to talk first, and then Stefania. And Jonas is another master colleague from University of, he's going to, I'm sorry, University of Pompeu. You have to remind me the name. I just blacked out my head. Pompeu de Fabra, right? Yes, and he's going to talk to us about monitoring of sites in Sindh region of Pakistan, and that's the work that he's been doing, and kind of with a comparison of when he also went to the field to do some field assessment. Thanks, Jonas.
Thank you. So hi everyone, my name is Jonas. I'm a postdoc in one of the partners of the MASA project, Pompeu Fabra University in Barcelona, Spain. We have mostly been working in the province of Sindh in Pakistan, and I'm going to show you some of the results of our work, including field work that we have done earlier this year. So as you know, one of the essential parts of the MASA project is the georeferencing, compilation and georeferencing of historical maps of the British Empire. And I have been doing some of that work in the province of Sindh in the south of Pakistan. And you can see in the image the extent of the historical maps that I have georeferenced. And as part of that work, I have also been identifying, as you probably are aware of, I have been identifying some features in these maps that are potential archaeological sites. And I have identified over 450 potential sites in the form of mounds drawn with hatchers. And you can see an example in the slide. And I have also been comparing those with satellite imagery. And some of the best known sites in this region include Mohenjo-Daro, that probably everyone knows. Jukarjodaro and other sites that are mostly mounds, they are tells, and they are very visible in satellite imagery, which means that probably by assessing freely available imagery like Google Earth, we could potentially match the features that we are seeing in the historical maps with sites on the ground, and then go to the field and do an assessment of those to ground truth them. That is to make sure that they are actually archaeological sites and not natural features or something like that. And in addition to prehistoric sites from the Harappan period, like Mohenjo-Daro, Jukarjodaro, we also have medieval sites and Buddhist period sites that are also mounds. And I'm showing some examples of previously recorded sites in the slide, Kaujodaro, Agamkot. So we have different periods represented by these features, and our idea was to look for some new sites using both the historical maps and the satellite imagery. So here are some examples from my work of possible sites that I have identified in the historical maps for you to see how different they look in the satellite imagery. So in some cases, it's quite obvious that we have some features still preserved on the ground, but in other cases, it seems that the images that appear in the historical maps do not really match anything anymore, because either those sites were destroyed or these are not archaeological sites at all. And so the idea was to have a sample of that and go to the field and look for both sites that are visible in the satellite imageries, but also sites that are no longer visible, but that might have been there, with the hope that maybe we would identify some feature on the ground, some remains, artifacts, or something like that. Okay, so I'm going to show you some of the results. We have visited earlier this year two regions in the north and in the south of the province of Sindh, around the districts of Larkan and Khairpur in the north, and around Hyderabad and Mirpur Khas in the south and surrounding districts. And we have been able to visit 20 sites based on satellite imagery and on the historical maps, the majority of which were still preserved on the ground. They were still visible as mounds, but some of which were no longer visible. And we also have some examples of features that are in the historical maps that do not really correspond to archaeological sites. They are actually natural features. So I'm going to show you examples of each one of those categories, and I'm going to end with some general assessment of the preservation of those sites. So here's an example of a site that you can see how it is represented in the historical map, and what it looks like on satellite imagery. This was a potential mound, but it turns out that it was really a natural feature. This was very close to the Rory Hills, so this was really a natural formation, a rock outcrop. And some examples of sites that are no longer visible on the ground, but appear in the historical maps, and they have some remains still visible on the ground. This is an example of a mound. You can see what it looks like in the satellite imagery, in the historical map, sorry. But in the satellite imagery, you can already see that probably there is nothing left. And when we did the assessment on the ground, we saw what seemed to be some reuse of ancient structures, because some historical bricks were identified, probably dating to the medieval times, the Calora period. And here is another example of a mound that is clearly identified in the historical maps, but when you look at satellite imagery, there is nothing that really matches that feature. And when we got there, there was really nothing left on the ground. But this is a minority of cases, right? So in most cases, we still have some features left. And in the cases where we identified a mound on the ground, we did some surface assessment, and we follow different strategies depending on the terrain and depending on the time availability. And also on the distribution of the artifacts on the surface. So sometimes we only did an opportunistic assessment on areas with concentrations of artifacts on the surface. In other cases, we did a more systematic survey by doing cross-transects, and also a combination of both cross-transects and then an opportunistic survey in areas of the site that had a great density of artifacts or some other features of interest. So now I'm going to show you some examples of those sites. Again, you're going to see what they look like in the historical maps, what they look like on historical on satellite imagery, and what we found on the ground. So especially in the southern part of our survey, in the surrounding of the districts of Hyderabad and Mirpur Khas, many of the sites that we visited were currently being used as graveyards. And that's probably one of the reasons why they were still preserved. And the entire land in the surroundings is being used for agriculture and other purposes. But these elevations, because they cannot be used for that purpose, instead of leveling them, they are reusing them as graveyards in many cases. So this is an example of a site that you can clearly identify on satellite imagery, and that matches very well what we see in the historical maps as well. And here you can see some examples of the artifacts that we find on the surface, ceramics that are being reused in order to cover the graves. And so here is another example. And the interesting thing about this site, if you pay attention to the satellite imagery, you will see that many of them have this representation of a tomb, and that's to indicate that they were being used as graveyards already when this survey for the map was done. And there are many details that obviously you're not going to get from the historical maps, but you can see them in the satellite imagery. For example, this site has a feature that is preserved in the middle of here. You can see it. That is higher than the rest of the mound, and you can see that in the photo on the top right corner. And here is another example. Oops. Another example of a site being used as a graveyard. So this is very typical of this area that we visited, and you can see how the ceramics is all being reused to cover the graves. And this is another example of a site with some architectural remains. In this case, we had the remains of a medieval mosque that was still preserved, even though there was no indication in the historical map of any kind of remnant structure. And so one of the most interesting things is to see how these sites are actually being affected now by current land use. So in this example, you can see how practically, more than half of the mound was probably destroyed by agriculture, and you can see the expansion of the cultivated fields, how it's basically eating the site little by little. And this was also a very frequent occurrence. Another example of that, so in this case, you have a mix of canals, irrigation canals that are being built that are cutting the site, and also the reuse for agricultural purposes, and also part of the modern settlement that is being built on top of the site. This is another example that is very interesting because you can see that basically from the historical map, all we have is the indication of a potential mound and this little X that marks abandoned villages. So probably there was an abandoned settlement when the map was done. But from the satellite imagery, you can already see possibly some structures that these are actually walls that surround the entire site. And you can see on the ground what they actually look like. So this, and finally, one example that I wanted to show, because this is one of the sites that was being most affected by current land use. So this basically was a site that was being exploited by a nearby industry. They were digging it for soil, to use the soil. And in this site, we have also found some evidence of looting. I'm going to show you in the next slide, probably. Yeah. So what are the most urgent or the most common threats to the archaeological sites that we identified in this area? Well, in the case of sites that are being used as graveyards, obviously the digging of new graves is disturbing at least the surface of the site. So at the same time that the use of the sites as graveyards is helping to preserve them because they're not going to be completely leveled, you do have a level of disturbance that results from the use as graveyards. The most common, probably in addition to the use as graveyards, is the agricultural expansion that is in many cases already starting to eat up part of the sites. And then in some cases, well, we have quarrying in the last example that I showed. And we also have a few cases where looting was very evident, people digging the sites to remove some artifacts before we arrived. And then just to show you some general assessment of the overall condition of the sites, you can see that most of them were actually not very well preserved. They were in pretty bad conditions, with the use as modern cemeteries and also leveling and construction being, and agricultural activities as well, being the most common factors of destruction of these archaeological sites. So with this, I conclude. Thank you. And if there are any questions, I'll be happy to answer them. Thank you.
Thanks very much, Jonas, for this great overview. If you have questions, please raise your hands. There is a question in the chat box from Heba, Jonas, asking how you could differentiate when at the site that you mentioned, Gabi. I don't know, Heba, if you want to unmute yourself, because she's saying that how you can differentiate between the currently used grave and historic grave.
Some of them had inscriptions, so some of them had dates. We found at least a couple of cases of that. Also, the ceramics, you can see that there are some very recent ceramics mixed with the old ones. But we found some early graves as well. There was one site that we visited that had the remnant, only one remnant, okay, of a Mughal period tomb. Probably there were more and they were looted. So actually, yeah, you have multiple time periods in some of these graveyards. Some of them are being used for a very long time. Yeah.
Thanks, Jonas. Muazzam, can you unmute yourself and ask your question?
Yeah. Hi, this is Wakar. Actually, I have an issue with system.
Sorry, hi,
Wakar.
Wakar.
Yeah, we both are together on one system. So my question with Jonas, lovely from Pakistan. You have your first field visit, I guess earlier this year. My question is, like, what exactly when you went to the sites, archaeological sites, what exactly was your just looking, taking pictures? Hi.
Yes, we were using the ODK data collection tool, and we were walking on the surface and taking pictures. For example, in the cases where we did cross transects, regularly spaced, we were taking pictures and sometimes sketching the artifacts and recording from a predetermined form everything from each unit that we were recording along the transects, and also about the site overall, taking pictures of every transect unit and also of the site. And then all of that was automatically uploaded to the cloud. So that's how we did this.
Yeah, basically my question was about the transect, and you already answered that. and hopefully we'll be practicing that in the Cholistan region soon. Yeah, thank you.
Great, thank you.
Thanks very much, Babar, and thank you, Jonas. So if there are other questions, you can type your questions in the chat. I know that Jonas needs to leave us shortly, but I'm gonna direct those questions to Jonas and put you in contact with him if you have other questions. Thank you.
Thank you very much.
Thanks, Jonas. Our next speaker is Dr. Stefania Merlo from Maysan Project, and she's going to show us examples from Africa, monitoring of sites and kind of change detection, and few examples from Africa. Stefania, over to you.
Thank you, Azadeh. Let me start trying to share the screen.
We can see your screen and we can hear. Oh, you stopped it.
It was on screen. Okay, yeah. Oh no, it was the correct one.
It was the correct. Yes, and it's in a presentation mode. Thanks.
Okay, thank you. Good afternoon or good evening, everybody. And I'm going to basically go through some site monitoring examples using remote sensing across Africa. When I started preparing this talk, actually, I thought I would find far less examples, but in fact, there is a growing literature on how remote sensing can be used specifically for heritage management in Africa. So I'm very happy that I have quite a range of examples and to share them with you and to give you the references. So it's basically a talk about interesting colleagues into what could potentially be done using remote sensing in terms of monitoring African heritage using remote sensing and giving pointers to where people can go. Of course, now it's not going to the next slide. I'll do it like this. So before I go into the archaeological examples, I also want to give you a brief overview about how remote sensing is actually used for monitoring various types of phenomena in Africa as a whole, because there is, in fact, a lot of work that has been done in the continent about monitoring other heritages or other phenomena, which actually we can borrow from, both in terms of final products that are available to us as archaeologists to use together with our archaeological knowledge, and also in terms of techniques that have been used for the monitoring. And so we will very briefly cover monitoring techniques, and then I will give you the case studies, as I said. So what is being monitored in Africa with remote sensing? And as you can see from this slide, this is like a minimum percentage of what is being monitored in Africa using remote sensing, and it ranges from urban expansion here in this slide in the middle to flooding, to carbon stock and carbon loss, to biome changes, to flood occurrences, to heat, to forest modifications, to fires, to deforestation and other phenomena like that. So a lot actually is being monitored in Africa using remote sensing. And there are huge projects, both at continental level and at regional and national levels, that are looking at a variety of different phenomena that can be monitored using remote sensing, and in particular, the ability of using time series, okay, to look at what happens in a particular part of the landscape through time. So this is basically just a brief list of all of the different phenomena that have been used, have been monitored in Africa, starting from over 20 years ago using remote sensing. And I'm gonna ask, let's see if somebody volunteers. Can you see anything missing from this list that jumps to our eyes?
Yeah.
So I know that people are shy, but basically there's no heritage here. And so as much as there has been a lot of work on using remote sensing for monitoring all sorts of things in Africa, there has been more limited work into the monitoring of heritage. Something that goes close to what we're interested in is conservation. And as you can see here, this is a fairly recent publication from 2017. By the way, all of the publications are in the last slide, and I will be sharing the slides with you. And as you can see, there has been a growing literature on actually using remote sensing to monitor conservation, but this is the looser use of the word conservation, and is basically the majority of the literature here is on conservation of ecological heritage or biological, biocultural heritage, let's put it like that, but not heritage in the way that the MASA, MAESM, IAMINA projects conceive it when they're doing their monitoring. So as much as there is a growing interest in and awareness of the fact that we need to conserve our heritage more loosely, both natural and cultural heritage, and we can use remote sensing to do it, this still remains a minority. So I just wanted to start from here and go into then when it comes to archaeological sites and monuments, knowing that there are these gaps, what is it that we can monitor? And there are a number of things that we can monitor using remote sensing, starting from, for example, and we can monitor different aspects of our archaeological sites and monuments. So there is a lot of work that goes on, and in part, for example, our colleagues in IAMINA and our colleagues at MASA have just demonstrated it, that we can do in monitoring the sites and monuments themselves. So we can, and this is actually a slide that looks at the impact of climatic stressors on outdoor cultural heritage, and look at what are the stressors that could actually be monitored, ideally using remote sensing, and that will have an impact on the single monument, on the single archaeological site. So this is what we can monitor, and we can use remote sensing to do it. Another thing that we can monitor using remote sensing, nevertheless, is what is happening to the surrounding landscape to our archaeological sites and monuments. So as you can see, there are two different aspects of the monitoring that we can concentrate on and that we can use remote sensing for. In this case, again, this is a list of changes in the natural physical environments that can affect cultural heritage in terms of landscape. So not just the site and monuments singularly, but the landscape that surrounds them. And again, there are remote sensing techniques that can look at that. And again, what is interesting here is that with remote sensing techniques and with the same type of imagery, we can use different approaches and different algorithms, depending on whether we're interested into what is happening to the single sites, or whether we're interested into what is happening to the larger landscape, because with time, what is happening in the largest landscapes may then have effects on the site and the monument. And so it gives us also a perspective on the fact that remote sensing can be used at different scales to monitor sites and monuments per se, or the broader landscapes in which they exist. I've given you here some examples of all the hazards and threats to sites and monuments and the landscape that can come from climate change, but there are other impacts and threats that we can monitor and that we do monitor that are non-climate related, such as natural phenomena, including natural disasters, illegal and damaging activities to sites, expansion of human-related activities such as agriculture, forest logging, livestock farming and grazing, infrastructural development, or tourism and related activities. These also have an impact on our archaeological sites and monuments and the landscapes within which they sit. And we should be able to try and see if there are remote sensing ways in which we can actually monitor this whole plethora of different impacts and threats that we can have on sites and monuments and their landscapes. What is interesting is that all of these threats and impacts leave a trace on the surface of the earth and can be explored via imagery and techniques applied in other environmental monitoring situations. In other words, we can heavily borrow from the body of literature and from the case studies that exist in other areas that I've showed earlier on to you, and apply this imagery and apply these techniques to monitor different types of impacts and threats that are happening to heritage. And just as a way of warning people as they think about how to monitor as managers sometimes of archaeological sites and monuments, the areas that they're interested in, is also to flag that different threats can be monitored using maybe the same imagery, but applying different techniques. So one really has to look at a series of case studies and apply their mind, because I've only shown a minimum part of the threats that can affect archaeological sites and monuments, but they are different. And some of them are quite complex and interrelated. And it is not as simple as saying, oh, okay, I'll just make a generic map of this area and I will be able to see what is happening to the archaeological sites from very different angles. In other words, monitoring at the same time flooding and fire and human activity, because they all require different types of methodologies and techniques to be highlighted. But once one starts creating maps that monitor different threats in a landscape, they can also be overlaid in a GIS and looked at cumulatively. So that's also the power of remote sensing. It gives us a tool that restitutes to us maps that can be overlaid in GIS software and can help us understand better what is happening to the landscapes. Importantly, how do we monitor using remote sensing? I've already alluded to it. We use imagery. And what is good, we can use historical imagery that dates back to the 1960s, like these corona imageries that you can see here. And then very recent multispectral imagery that shows us things in color from the 2000s and 2010s onwards. We can use different techniques to monitor possible threats and impacts on archaeological sites and monuments and landscapes. We've seen a lot of examples of visual inspection, and I will also show you a lot of examples of visual inspection. But there are other techniques that we can use that we borrow from remote sensing to monitor these threats. Land use and land cover classification and change detection is something that we heard about today and is the technique that we can use. But for example, we can monitor the progressing of certain threats using remote sensing derived indexes, like vegetation indexes, water indexes, soil indexes that will show us how flooding is happening, how the vegetation is changing around the site, how the areas around the site are being eroded. So that's also a way of looking how to monitor archaeological sites and their preservation. And then obviously there is complex modeling of different parameters through the integration of remote sensing data and GIS analysis that can be applied. So we don't only have one technique, as I said, we can have different and increasingly more sophisticated and complex techniques to use that can also be combined together. And as you will see, the majority of the examples in an African context are more limited to visual inspection, but it's just because we are at the beginning of exploring how remote sensing can be used for monitoring threats in an African context and globally, to be honest with you. There is a lot more potential there. So this is an overview of the case studies. I will only give you a snippet so that you can see some images and some of the things that have been detected. This is a kind of summative slide that shows some case studies across Africa. Obviously, I had to extend into the MENA region of Africa because a lot of the work has been done by our predecessors, in particular, actually, MENA, on what is the impact and how can the monitoring of the impact at archaeological sites and monuments can be done in North Africa. So I take the definition of Africa here the way I prefer it. You know, it is an entire continent. It's not divided in bits and pieces, and so I offer you different case studies. So a lot has been done on monitoring archaeological damage that can come from urban and other infrastructural developments. I'll show you some of this. We have also monitoring of archaeological damage from agricultural expansion, monitoring and quantification of looting activities, monitoring of preservation and damage due to natural phenomena and anthropic activities. So we have quite a number of case studies that cover different things with different techniques. So in terms of infrastructural development, this is a case study at which I worked quite a while ago with a colleague in Botswana that was looking at how we can use Google Earth imagery to monitor basically how archaeological sites, which are the small red dots that had been identified in the area of Gaborone, a very fast expanding city from the 1960s onwards, and what would have been the impact, okay, of urban infrastructure developing in this area through time. And as you can see, we start from 1986 and we come all the way to 2016. And you can see here the gray area is the area that was built up, and through time, that built up area actually became more and more extended. And it basically went on to cover and sometimes destroy archaeological sites that had been actually recorded before and throughout this period. So very simple visual inspection using Google Earth Pro, and we can easily see how many of these sites actually have been lost. This is a case study of South Africa that also shows you the dramatic damage that infrastructure development, in this case residential area, can do to archaeological sites. These are two stone-walled archaeological sites that have been completely obliterated by residential expansion without obviously any knowledge of the heritage authorities that this actually was happening. This is the case from Libya, where the IAMINA team has looked at, again, urban expansion near the archaeological site of Cyrene. And you can see the contrast here between corona imagery from the 1960s and recent imagery from 2016 here of the infrastructural expansion near the city of Cyrene and going to encroach on the south necropolis, the south cemetery of Cyrene. Again, visual inspection with ground verification and sites that had already been found by IAMINA, and an assessment of how much the damage had been done to these archaeological sites. And then also some, let's call them more advanced automatic classification techniques. In this case, Rain and others used unsupervised classification techniques to actually demonstrate how urban expansion developed through time from the 1980s to 2017 in the area around Cyrene, and obviously impacted on the preservation of the archaeological site in this area. So you can also use semi-automatic techniques and automatic techniques to do so. This is the work by Nadia in Ethiopia in the area of Arla and Arar, again, tracing on Google Earth the urban expansion and the building of residential and other buildings, and starting also to quantify in terms of aerial coverage how much of a World Heritage Site in this case has been encroached by buildings. And these become very useful documents also for policymakers and for heritage managers to demonstrate that things are happening and archaeological sites are being overtaken by urbanization events. And this allows us to do it over larger landscapes and plan for larger landscapes when we have very few people on the ground that are actually able and go and check in person what is happening at the site. This is a case study very recently published about the impact of other infrastructural development or potential impact of infrastructural development on archaeological sites. And this is the case of the Gerd, which is this planned dam system in Ethiopia, and how remote sensing can be used to look at the impoundment of water of various areas and then start calculating what parts of heritage sites are impacted and will be impacted in the future by the construction and impoundment then of dam areas. Moving on to archaeological damage from agricultural expansion, IAMINA has done a lot of work on this. This is just a summary of some of the work that has been done with the grid squares covered in this particular publication, and looking at where vegetation is present, where we have urban areas, where we have both and how many sites basically in their very large database have been damaged by agriculture. And again, this is a combination of manual checking of what is happening to sites, but also automatic techniques and various algorithms that the IAMINA team have been developing to be able to assess these impacts. Here are very important, again, some multi-temporal images of various areas. Here we are in Libya, where you can quite clearly see what has happened to these archaeological sites in 2009, untouched by agriculture. Then the agricultural fields start being laid out and agricultural activities start. And this is bang where archaeological sites had been identified by IAMINA team previously. And as I said, other work that has been done here in terms of monitoring is the site can be analyzed also using algorithms that check for each site which ones have been damaged, and then also can help you to analyze numerically how many of these sites, after having checked them in the field, are true positives. In other words, are sites that were really damaged. Which ones were false negative? In other words, the algorithm told us that there was no damage here, but in fact damage had been made. And true negatives, in other words, sites where no damage had been done, and the algorithm picked that, and in reality on the ground this was the case. And again, this allows us, when you start applying algorithms that detect these changes in the satellite imagery, you can do much larger areas, and then you can just sample the number of sites that you want to go and visit and verify to check if these damages have in fact happened. Looting activities, as you can see, this is a paper that was published in 2019, and that is summarizing how remote sensing has been used to monitor looting activities in various parts of the world. And sadly for us, this monitoring has only happened in North Africa as an area of interest to us, and I can't see any papers that they have found for what concerns India and Pakistan. And so it would be very interesting, I think, for us to go and look at what techniques can be used to monitor looting and actually start publishing what we're finding in our areas to make actually this very biased map much, much richer going forward. These are just examples of how looting activities can look like on a barren environment in the desert with all these holes, as you can see, that you see in the landscape and in the vegetated environment. And again, just a few case studies. This is the work of Parker and others in Egypt from 2016, where they actually manually counted pits, what they appeared like holes near archaeological sites in Egypt. And then the publication of superpixel and pixel-based classification for the identification of looting in these areas. And finally, a response actually to the 2016 paper by Parker, by Fradley and Sheldrake, that also tell us a cautionary tale about using visual inspection of very small areas for monitoring looting, because that can basically result in huge errors in the interpretation of your imagery and seeing looting where in fact looting didn't happen. And the recommendation that it is important to have very large databases and looking at these activities a bit more in detail to differentiate what really is looting or other types of damage or no damage to archaeological sites. Again, the last two case studies, monitoring of preservation and damage due to natural phenomena and anthropic activities. This is work that we have started doing with the Mayasam team in southern Ethiopia and northern Kenya, using basically land use, land cover mapping of time series, and then calculating here in the graph, you can see the percentage change of the different land use, land cover types, and how this may or may not have impacted the use of traditional wells in southern Ethiopia and northern Kenya. And we have actually found a correlation between use and disuse of the wells and the expansion is in particular of urban and agricultural activities, which are a main problem for archaeological sites all across Africa. This is another very interesting paper that has looked at the impact of coastal changes to World Heritage Sites along the coast of Africa. It was a very complex paper that was published actually in Nature, and is looking not only at how sites may have been impacted in the past 40, 50 years, but is also predicting in the future, under different scenarios of climate change, how coastal sites may be impacted in the future. And again, you can use remote sensing. I mean, remote sensing has been used heavily here, not for doing the monitoring itself, but for creating all of the layers that are used for the monitoring. So the coastal erosion layers, the marine ingression layers were all created using remote sensing data. Digital elevation models in particular, but other corollary data. So again, this case study also helps me explaining that we don't necessarily use remote sensing sometimes for the direct monitoring of the threats, but we use remote sensing for creating those background layers that are necessary for measuring the impact of certain phenomena on the sites, okay? So there are two levels at which we can use remote sensing. I'm done with my presentation. I'm going to share it because I think there is quite a lot of richness there in the case studies that I very briefly presented. Most of them are actually open. They've been published as open publications, and I would recommend that you refer to them and go and read the details of the different case studies, the type of imagery that has been used, and the techniques that have been used to monitor these very different threats and impacts to archaeological sites. In this case in Africa, but the same techniques can be applied elsewhere. Thank you very much.
Thanks, Stefania, and yes, thanks for mentioning this. We're going to share the presentation, the PDF format of the presentations on our joint Google Drive, and in the email I'm going to send to all the participants, so you can have access to the references and all the slides as well. Before giving you some time to ask a question, and if you have other questions, you can type into Stefania. I understand that we've passed our finish time, so I'm going to. I've also apologized in the chat, and I understand if you have other engagements and need to leave us. But before doing that, it would be very important for us if you can answer the poll that we started at the beginning. So the first two questions are the same two questions we asked at the beginning, and it has two other questions. You should be able to see it, and if you can answer it. And in the meantime, if there are any questions to Stefania, you can unmute yourself and ask your question, please. So we can do both at the same time. Thank you. And I'm going to check the chat and see if there are any questions for Stefania there. Any questions? We're going to have a final short presentation, and that's sort of an opening to a document that we want to produce as a result, to give you a reference to go to find sources for the imagery. And Stefania has worked on that, and she's going to present that work to us, but as a intro, kind of a work in progress, and we're going to make a document and share that with you. But before starting that, I'm going to wait another. I have, how many I have? I have 50 people out of 100. So if you can answer another minute, and if you have questions, you can ask, and then we're going to ask Stefania to present our last presentation of the day. Stefania, do you want to share your screen? I'm going to end this after you sharing, kind of leave a bit more time, but doing.
Yeah, thank you. And I realized my camera was off all along.
Yes, it was.
you my gesticulation. So I'm putting it on now.
Thank you.
Share the screen. It's going to be very brief. Of course, as I was preparing the other presentation and also this document at the same time, can you see it?
No, Stefania.
Anyway, let me try again. Now?
Yes.
So as Azada was saying, this is work in progress, and it was basically out of the consideration that we made that many archaeologists are daunted by having to think about using remote sensing or remote sensing imagery for their work beyond, you know, the availability of Google Earth or Bing. So we thought, why not producing a document where we put together information that may be useful for archaeologists and practitioners so that they can easily look at what is available in terms of remote sensing imagery to archaeologists and where they can go actually to find and download all of these resources for themselves. So one thing that I started doing is to start putting together a list of remote sensing imagery that is available. In this case, this is a summary table with multispectral sensors and imagery. Sadly, as you can see from my symbolization, the majority of this imagery is not available for free. So the only imagery that is available for free I have highlighted in blue in this table and is Landsat and then the Sentinel series. But a lot of other imagery is also existing there, and some commercial companies do give educational access to a certain amount of the imagery to universities and other educational enterprises. And I thought, okay, once a person knows what imagery is available and checks at what resolution they may want that imagery, they can approach these companies and go to their websites to ask for access to it. So these are various tables that put together different types of information. Also, I don't know where I will put this, but I really like this slide because it gives you an overview of the Landsat series, which are for free, downloadable for free, and are very useful for monitoring when they started in the 1970s, as Pamela had mentioned, and where they are continuing. And they also tell you which type of imagery was available or is available when, so that you can start constructing, for example, your own time series. This is another classification with different characteristics of imagery that you'll be interested in. And here we come, I think, to the part that people would probably find useful. We've made the list of the principal repositories for the download of imagery and products. Bear in mind that when it comes to remote sensing data, you can choose to download the raw images, but you can also choose to download, because they're now available at a global, at a super regional, and at a regional scale, a series of pre-packaged products. In other words, if it is not necessary, if the scale at which a land use land cover map is available, you think is good enough for you, if you have limited resources, there's no point doing the land use land cover map yourself. They are available. You can go to various repositories, download these land use land cover maps, and then overlay them over your archaeological sites to see what has happened to them through time. So without having to go through the trouble of creating some of these products yourselves, they are actually available out there. And seeing the limited resources that we always have as archaeologists, it may be a good idea to use these products after having checked, of course, their accuracy and their quality, and apply them for our monitoring, for example. So these are the principal repositories for the download of imagery. The majority of it is actually imagery, not products. But in some cases, like NOAA Data Access Viewer, allows you to access imagery, land cover, and elevation and LiDAR data. All of these 8 websites that I have put here are all for the download of free imagery. Sample imagery can also be downloaded or accessed from commercial companies, and I've put here the website of these commercial companies that Under certain circumstances, and you have to contact them, allow you to access their data, which are very high spatial resolution data. For example, MAXA Open Data for Emergency Responses has just recently released imagery for the floods in Pakistan, because there was a request from, I don't know if it was the government or universities, to get access to this imagery for free, and it was released. Okay, so there is an opportunity of contacting these companies and get their imagery for free. Here we go from the accessing of the imagery itself to land use, land cover datasets. And these datasets are available at a global scale. Okay, and here you can see we were very lucky. There has been a publication that came out in 2022 that I reference in this document that has given a very fantastic overview of land use, land cover products globally and of their quality. So for each one of them here, I've prepared a table with a link to where you can download the data. But if you go to the publication, they also have done an assessment of each and every data set to explain what is the quality of the data set and to explain what you can use that data set for. Of course, it's also very important to look at what is the spatial resolution of the products, because you may not be interested in having a product that has got a spatial resolution of 1 kilometer, because it doesn't give you enough detail to monitor your sites. But if we come down to 30 meters or 10 meters, then maybe you'll be interested in downloading this product and see if it is good for you. These are all land use, land cover maps with single data. With a single data, it means that they only capture one moment in time, but we also have time series. So you can download pre-made land use, land cover time series globally. And then I started looking at what is available for our regions of interest. So these are the land use, land cover datasets available for Africa. And as you can see, you start finding datasets that come down to 30 meters resolution, because of course they're interested in a smaller region and therefore they can produce data at higher resolution. And these are all the products for Africa. Sadly, but here I will ask the help of the collaborators in Asia, you know, India, Pakistan, in subcontinent. I have only found a Himalayan regional land cover database that can be downloaded for free. And then obviously we have the decadal land use and land cover classification across India, which is a multi-temporal map 1985, 95, 2005 at 100 meter resolution, which is released by DAC. This is the US government. Then I also found that for India, for example, there is a National Remote Sensing Center that has land use, land cover portal. But to the best of my knowledge, and I'm sure you know this better than me, you can't download the maps. You can only interact with them through the portal, which isn't always necessarily useful if you want them to have these maps to do your archaeological heritage monitoring, but I may be mistaken. And so I would really like to work more with MASA to actually beef up this so that colleagues in various institutions across India, Pakistan can also find, you know, clickable live links to go and download data that is of interest to them. This other website that I put here is the remote sensing based index database. I mentioned that we can use indexes like vegetation indexes, soil indexes to monitor what is happening in and around our archaeological sites. There is actually a global index database with all the different indexes available and the possibility of downloading them for free at different spatial resolutions to explore again what is happening around your archaeological sites. And then here I started putting together the references so that you can go to the various publications that have done basically evaluations of what type of data is available out there and at which resolution, and starting also to assess the data sets. Because what is very daunting if you're not a remote sensing practitioner is that 10 different data sets are given to you, but you have no way, because you lack obviously the expertise. You're an archaeologist, not a remote sensing practitioner. You lack maybe the ability of assessing, you know, which data set would be best for you, which one is a data set of a good quality, and which one is a data set of not such a good quality that then I should avoid using. And as I said, there's a number of publications that are coming out that are doing that for us. These are remote sensing practitioners that are assessing the quality of various remote sensing based products, indexes, land use, land cover, classifications, and they're telling us, okay, this is the quality, this is the accuracy. Do you still want to use this product, or will you have to create your own before you proceed basically integrating remote sensing with your heritage monitoring in this case?
Stefania, we have Rajani's hand up, and I think she wants to comment on the sources for India's side.
Yeah, and I really apologize for the India sources, but it's a bit less of my area. So,
thank you. I just wanted to mention that the National Remote Sensing Agency, which has a portal called Bhuvan, does have land use, land cover for open for for visualizing. But they also, for selected area, if you give by district or at a district level, you can request them and they share vector layers with all the attributes and so on. This, of course, I don't know whether it is for Indian users or users from abroad. I've always used as an Indian user, and also there is a range of images also available from Indian satellite series, and for users within India, it is much more. The price is much less than if it is users from abroad. Just wanted to share that. Thanks.
Yeah, no, thank you, Rajani. And I think we should actually really integrate a table, because there are satellite missions in Asia and in Africa as well, and it would be good for people to know that they exist, and remote sensing agencies. That's a very good idea. We can integrate that table. And also just to flag that all of these websites that we've put there, they are in many cases for free imagery, but you always have to log in and give your credentials before you are given access to them anyway. Okay, so it's not just that you go to a site and you click, you have to do a few steps. And the same, even in some countries, you can download imagery for free, whether you're a citizen or not. And some other countries have got the same rules that you were mentioning, that, if you're a citizen or based in that country, you can get free access or very cheap access. And if you're not, it's a different story. So thank you for flagging that. I think we should write it up in the document.
Yeah. Can I just mention one more point? I have also found this as a very challenging way to present to a non-remote sensing analyst about how do you choose what image do you want, because in general the remote sensing community has been presenting images in a sensor point of view. They say this sensor can do this, rather than a user point of view. If I want to see this, then go to the sensor. So I have actually tried to put together a table in my book where I have tried to classify what sensor to go based on what feature you want to look for. I don't know how useful it is, but if anyone takes a look at it, please do give me feedback, which will help me for my next book. Thank you.
Thanks very much, Rajani and Stefania. So we're getting to the end of our session. Again, apologies that we ran a bit over. I shared a link. I showed 2 links actually on our drive, and I'm going to resend all the links to you in the email as well. One is for all the moderators with their emails in the Google Earth room. So if you have any questions, you can contact and ask them. If you have any general questions, you can always contact me, of course. The second link I sent you is specifically for the South Asia room, and those are the examples of the sites or site types that might be of interest for you to fly over, use the coordinates in Google Earth yourself and go and have a look around. And if you have any questions, you can contact us. And so thank you. Oh, before finishing, just a fun thing to do. I want to share this. The Padlet satellite imagery that that you all added with your location. So this is, you can see from different places that you joined us online, and it's kind of our workshop satellite imagery, let's say, of the places that we're all from. Thank you very much. We really hope that this workshop was useful for you to give an understanding of remote sensing and techniques in remote sensing. We're going to continue our workshops and sessions with everything that we see from our stakeholders and collaborators that might be of use for you. And we have other sessions, we're going to have other sessions organized. So don't hesitate to contact us if there are any subjects that you're more interested in and you think that we need to focus more on. Thank you all, and we hope to see you soon. And thanks I'm sorry, before finishing, I want to thank you to all of our speakers from both our guest speakers and also from MESAM and MASA side. Thank you all.
Thank you. Bye-bye.
Thank you. Bye.
Bye.
I'm going to stay here to say a few things, and then I'm going to end the meeting. Bye.
Thank you so much.